This is Hubble's original data from 1929. And this is one of the reasons he was such a great scientist, because he knew to draw a straight line through this data set, which itself is already not so clear. It's not obviously the right answer. But what he found was, in fact, that velocity is proportional to distance. Okay? And the great thing is he got the answer wrong by a factor of 10, which was an embarrassment at the time. Again, I'll throw a little commentary in it. Because if the universe were expanding this fast, you could calculate its age, and its age would be 1.5 billion years old. That was in 1929. Now, as anyone knows, if you read any of Richard's books, you would know that, well, by 1929, we already knew the Earth was older than 1.5 billion years old. And so it was embarrassing that the universe was younger than the Earth. One of the many embarrassments in cosmology that's happened over the years. And in fact, taken by some people to once again argue that science didn't know what it was doing. But the problem was, of course, he wasn't a bad astronomer or a bad scientist. The problem was trying to measure distance because he didn't have good standard candles. And that's, as I say, been the holy grail, if you wish, of cosmology over the last century. And we now have standard candles. Here's one. I wish there was better resolution on this projector. It's a beautiful picture from the Hubble Space Telescope of a distant galaxy, far, far away and long, long ago. And there's a whole galaxy. It's about 1 billion light years away. We're looking at it as it looked 1 billion years ago. So many of those stars no longer exist. And here's an object that's just as bright as the whole center of the galaxy. You'd think it's a star that's near in our galaxy that just got caught in the picture frame. It's not. It's a star on the edge of that galaxy that has exploded. And exploding stars shine with a brightness of 10 billion stars. They're the brightest fireworks in the universe, supernovae. And they're remarkable, and I keep having asides. Maybe I'll get to my point eventually. But this is something that I wrote a whole book about, and someone asked me yesterday why I wrote that book. Because it is the most poetic thing I know about the universe. Richard wrote a great book called, what's it called? Our Ancestors? What's it called? Ancestor's Tale, yes. I wanted to make sure I got that right. And I wrote a book that was a different Ancestor's Tale. It was called Adam. But the amazing thing is that every atom in your body came from a star that exploded. And the atoms in your left hand probably came from a different star than your right hand. It really is the most poetic thing I know about physics. You are all stardust. You couldn't be here if stars hadn't exploded, because the elements, the carbon, nitrogen, oxygen, iron, all the things that matter for evolution weren't created at the beginning of time. They're created in the nuclear furnaces of stars, and the only way they can get into your body is if the stars were kind enough to explode. So forget Jesus. The stars died so that you could be here today. Okay? And anyway, this is great. Anyway, so the real point of reason I showed this picture is that these objects, these exploding stars, are great standard candles. We can actually observe them amazingly, even though only one occurs every 100 years per galaxy. There are enough galaxies that if you put your hand up in the night away from LA and looked in a dark spot in the sky and made a hole the size of a dime, with a large enough telescope, you could see 100,000 galaxies. And that means that even though stars explode once every 100 years per galaxy, in that little region with 100,000 galaxies, on a given night, you'll see 10 stars explode. The universe is huge and old, and rare things happen all the time, including life. And so it's an amazing thing. And we can observe stars exploding, we can measure their brightness, we can measure their colors, and that has allowed us to produce a great standard candle. And after 75 years, we now can determine the expansion rate of the universe. This is a new Hubble diagram, much better than Hubble's. It was made after the discovery that on a log plot, everything is a straight line. But even still, we now know the rate of expansion of the universe to 10%, not a factor of 10. And we therefore, in fact, we now know the age of the universe through other things extremely accurately, to almost 4 decimal places. 13.72 billion years is the age of the universe. It's amazing that we can say that with a straight face and have scientific reasons to support that. Okay, great. So let's go back to Einstein. Einstein had this cosmological term. He said, it was my biggest blunder. I want to throw it out, get rid of it. But the problem is you can't get rid of it so easily. Because using the miracle of modern mathematics, you can rewrite that equation. And now this is a small step for a mathematician, but a giant leap for a physicist. Not because it's that hard to put this term over there. Most of us could do that. But because it now represents something very different when it's on this side of the equations. Here it was somehow a geometric quantity. When it's here, it looks like a new contribution of the energy and momentum of the universe. What could contribute a term like this? And we know the answer. Nothing. By nothing, I don't mean nothing, I mean nothing. If you take empty space, and that means get rid of all the particles, all the radiation, absolutely everything, so there's nothing there. If that nothing weighs something, then it contributes a term like this. Now, that sounds ridiculous. Why should nothing weigh something? Nothing is nothing. And the answer is nothing isn't nothing anymore in physics. Because of the laws of quantum mechanics and special relativity, on extremely small scales, nothing is really a boiling, bubbling brew of virtual particles that are popping in and out of existence in a time scale so short you can't see them. Now again, that sounds like philosophy, like counting the number of angels on the head of a pin, or religion, or something useless. I shouldn't say, Dan Dennett is here, I shouldn't say philosophy is useless, but anyway, he's also a friend. But the point is, we can't measure virtual particles directly, but we can measure their effects indirectly. And in fact, they're responsible for the best predictions in physics. Here, by the way, is actually an animation that was shown at the Nobel Prize ceremonies about 5 years ago by a friend of mine who happened to win the Nobel Prize for developing the theory that produced this. This is the space inside of a proton, the empty space inside of a proton. Not where the quarks are, but the empty space between the quarks. And this is an animation, but it's an exact animation coming from physical calculations. This is what the space looks like. Now, how do we know that? Well, there are a lot of reasons, but one of the things are, it turns out most of the mass of the proton comes not from the quarks within a proton, but from the empty space between the quarks. These fields popping in and out of existence produce about 90% of the mass of a proton. And since protons and neutrons are the dominant stuff in your body, the empty space is responsible for 90% of your mass. So these empty space is vital to science, and these calculations are vital to understanding not just protons, but electrons and atoms, and produce the best comparisons, and I will repeat this, the best comparisons between theory and experiment in all of science. To 10 decimal places in quantum electrodynamics, using these calculations, we can get the right answer. It's amazing. So, if that's the case, let's calculate the energy of nothing where there's nothing else. And when we do that, we come up with a calculation which is pretty bad. It's the worst prediction in all of physics. We calculate, you can't even see it, I think, there's a 1 at the end of that. We calculate that the energy of empty space is a gazillion times the energy of everything we see. That, as I say, is the worst prediction in all of physics, which is why we didn't talk about it for a long time. We calculate that empty space should have an energy of 120 orders of magnitude more than galaxies and stars and people and aliens and all the rest. And if that were the case, we just wouldn't be here. So we knew something was wrong with this calculation. It's been around since I was a graduate student. And we knew what the answer was. Theorists always know the answer. They're just sometimes right. We knew the answer was 0, because it's the only sensible answer. Because, you know, you can't cancel a big number like this. Let's say the energy of empty space was comparable to the energy of everything we see. Well, we'd have to cancel this big number to 120 decimal places and leave a finite answer in the 121st decimal place. No one knows how to do that in science. But 0 is a number we can get beautifully in science. We use mathematical symmetries. Things cancel, equal and opposite things cancel all the time in science because of symmetries of nature. So we knew the answer. We didn't know what the symmetry was, but we knew the answer was 0. And we could go to bed at night and that was fine. But you know, the neat thing about cosmology is it's really a science. And science is empirical. Knowing the answer means nothing. Testing your knowledge means everything. And so the question is, we should test what the energy of empty space is. And how can we do that? Well, we weigh the universe. How do we do that? We stand on the shoulders of giants. This is a picture I took in an island off Sweden, which used to be an island off Denmark now, which used to be an island off Sweden. It's the island of Ven. I think I said that right. And this guy, if you look carefully, he doesn't have the end of his nose. His name is Tycho Brahe. And he, as many of you know, laid the basis for Newton's law of gravity by doing nothing other than spending 20 years on his back, a noble tradition, in this case, looking up at the sky without a telescope, measuring the positions of the planets around the sun. And then he was a crummy feudal lord. He got kicked off that island. He gave the data, went to Prague, gave the data to a hapless assistant named Johannes Kepler, who again spent 20 years without a Macintosh trying to interpret the data, and fudged it, we now know, and came up with, of course, Kepler's laws, which led to Newtonian gravity. And the point is, we can use gravity to weigh the universe, including the weight of empty space. Now, why do we care? The reason I got into cosmology. General relativity tells us that space is curved, and therefore the universe can be one of three different geometries: open, closed, or flat. Now, I can't draw pictures of three-dimensional curved universes very well, so here are pictures of two-dimensional curved universes. This is a closed universe, a sphere, a surface of a sphere in 2 dimensions. But if we had a closed three-dimensional universe, it's very simple. It'd be very similar. If our universe was closed, if we looked far enough in that direction, we would see the back of our heads. Light would go around the universe. And an open universe would be infinite in spatial extent, as would a flat universe. And that sounds really nice, but it's irrelevant. The really important thing is, in a universe full of matter, a closed universe will expand and stop and then recollapse in a big bang, in a big crunch, the reverse of the Big Bang. An open universe will expand forever, and a flat universe will expand and slow down but never quite stop. And that's why we wanted to know which universe we live in. And as I say, that's why I wanted to learn about it, because once I knew which universe we lived in, I would know how the universe ended. Okay? And so, weighing the universe tells us what the curvature of the universe is, and that's why we want to weigh it. So here I want to just show you in the next few minutes how, in fact, some of the most remarkable developments in cosmology, and then tell you how they completely changed our picture of the universe so that we understand that the universe we live in is the worst of all possible universes to live in. Okay, just so you know where we're heading. This is a cluster of galaxies. Each dot in this picture is a galaxy. Again, amazing to think about. Remarkable. Every one of these galaxies contains hundreds of billions of stars, and perhaps civilizations, some civilizations that are mired in religious gunk, other civilizations that have moved beyond, and other civilizations that are long dead, because this is about 3 billion light years away. 3 billion years ago is when that picture was taken, basically. Now, clusters of galaxies are the biggest bound objects in the universe, so if we could weigh them, we could weigh all the mass in the universe, and we can weigh them now. We can weigh them by using general relativity. Because in this picture is a remarkable phenomena that Einstein first predicted in 1937, though he said it would never be observed. He underestimated observers. If you look at this picture, you'll see these blue things, these weird blue things. That is a phenomenon that we now understand as gravitational lensing. Einstein told us that a mass will curve space around it. And he realized, therefore, if you had a big enough mass and you have a source of light behind that mass, the light can bend around that object and come back and be magnified, just like my glasses magnify things. Or, like a cut glass goblet, if you look through it, I'd see many images of this room. Mass can act like a lens and magnify things and split images, and that's precisely what we're seeing. All of these blue things are different images of a single galaxy located about 3 billion light years behind this cluster. Gravity is magnifying the image, distorting it, and bending it. Remarkable. Truly remarkable. But because we understand general relativity, we can work backwards and figure out how much mass must be in that system and where it is in order to produce that image. We can weigh the system using general relativity. And when we do that, here's an inversion by Tony Tyson, who's now up in Davis. This is the system, and the spikes are where this is where the mass is in this system. The spikes are where the galaxies are. But you notice most of the mass in this whole system of clusters of galaxies is not where the galaxies are. It's between the galaxies. It's where nothing is shining. About 50 times as much mass in this system, and in all systems we can measure, comes from stuff that doesn't shine. And physicists, with their linguistic perspicacity, have called it dark matter. And we now understand that 90% of the mass of galaxies and clusters, including our own Milky Way galaxy, is made of stuff that doesn't shine. And that isn't maybe that exciting, because there's lots of things that don't shine. You don't shine if I turn the lights out. Well, those of you from Los Alamos might, but the rest of you don't. But